Solving trigonometric equations is precisely the same in concept as solving equations from the past. That is, we have some variable involved and we're looking for the value or values of the variable that will cause the statement of equality to be true. Consider this problem. Now, notice that the variable involves sign. So we have sign of some variable, and we have some other stuff here. Well, we'd like to isolate the sign of x before we evaluate the value for x. And it's pretty easy to evaluate x once we have done that. Adding 1 on both sides, we get 2 sine x equals 1. Dividing on both sides by 2 to clear this coefficient, we find that sine x is equal to 1/2. Now, so the sine of what angle, or the sine of what real number, is equal to 1/2 is what this is requesting. Now, let's find an exact value, and let's evaluate this using our little triangles for reference and our unit circle, and we could use a graphing approach to analyze the situation, and all of those ideas will come in handy in this situation. Well, the first thing we might think about is that, well, let's see, the sine of some angle is 1/2, and I know that that angle is found in some little triangle having to do with this 1, 2, square root of 3 business, and the 30-degree angle is here, and from the perspective of that 30-degree angle, the opposite side over the hypotenuse is 1/2. So, aha, it's a 30-degree angle here that I'm talking about for x, or it's an angle of pi over 6. So x is either 30 degrees or pi over 6. Since it's a letter that's being used here, not a theta symbol, I'm going to assume that it's pi over 6 that we're looking for. So I'll say x is pi over 6. Now, we want all the values of x that will make this true. And we know that if we examine the unit circle situation, that sine is positive in this quadrant and in this quadrant, but negative in these two. So maybe there's an angle in the second quadrant that also makes this true, and certainly there is. You see, we have found the angle in the first quadrant. This 30-degree angle makes that true. But there's a reference angle of 30 degrees in the second quadrant that also makes that true. Now, a reference angle of 30 degrees, but what's this angle? That's the angle that we want, because it's the sine of this angle that will also be 1/2. Well, let's see. If we're talking 30 degrees, then this angle would be 180 minus 30, or 150 degrees. If we're talking about pi over 6 for the reference angle, and we know it's pi up to here, then pi, or it's 6 pi over 6 minus 1 pi over 6 is 5 pi over 6. So an angle of 5 pi over 6 would also make this true. Are there any others? Well, sure. Every angle which is coterminal with these two will also make this statement of equality true. That is, if we're right here, then an angle which goes all the way around and back to that spot, you see, will make it true. And go around twice to that spot, and it'll make it true, and so on. And the same idea for this. So we can generate now the infinitude of answers, the infinite idea that we have a whole bunch of values of x associated with pi over 6 and a whole bunch associated with 5 pi over 6 that make this statement of equality true. So let's generate those. It would be pi over 6 plus, now let me emphasize, I want to make sure we understand that where I'm going with this conversation, that it is pi over 6 and then pi over 6 plus 2 pi, you see, go all the way around the circuit, and then it's pi over 6 plus 4 pi, you see, and then pi over 6 plus 6 pi, and so on. So we want to write some statement that gives all of these values in one little statement. And to do that, and I think we've seen the notation before, but it's pi over 6 plus n times 2 pi. You see, n being an integer. Now that integer, you know, can be positive or negative, so we could generate values in either direction. You see, and this gives the infinite answers associated with pi over 6. And with 5 pi over 6, same idea. Now, a lot of times this part of the problem is rearranged. These factors are rearranged, and it's 2 pi n or 2n pi, something like that. So we could write this as, in another way, as 2 pi n if we wanted to do that. Consider this problem. Now, notice here that this one is quadratic. And when we have a quadratic situation, we have to think in the world of quadratics from our experience. Now, notice that we have a second degree term involving cosecant x. And we understand that, and I want to make sure, and I haven't emphasized this in the past maybe enough, but this cosecant squared x means the same thing as cosecant x squared. That this notation means exactly the same as that. You see, and we just put this little 2 in between here so that we don't have to write the parenthesis all the time. All right, let's make sure we understand that because it gives a quadratic nature to the equation. Now, because we have a second degree term involving cosecant x and no first degree term involving cosecant x, we can use the idea of extracting square roots, or use this square root property. And we do that by isolating this term on one side of the equation and the real number on the other side. So I'll add 2 on both sides to get this. And now, by extracting square roots, I know that the cosecant of x is plus or minus the square root of 2. Now, again, we go through this analysis process thinking about our little triangles and the unit circle and all of that kind of thing. And I think we might remember that this situation is associated with the 45-degree angle. And it was 1, 1, the square root of 2. Now, for cosecant, remember it's the reciprocal of sine, and sine is opposite over hypotenuse, so this is hypotenuse over opposite, so it's the square root of 2 over 1. So a 45-degree angle is what we're thinking about. And then we imagine this in the unit circle idea, and it's a 45-degree angle in this quadrant. But now cosecant, it doesn't make any difference about sine pattern here so much. I mean, we could say cosecant goes with sine and it's plus, plus, minus, minus. But we're talking about plus or minus the square root of 2. You see, so we have a reference angle in the second quadrant whose cosecant, this reference angle, is associated with that angle. And the cosecant of that angle then is the square root of 2. But we have a reference angle over here, and we have one over here as well. You see, we have a reference angle there and a reference angle there. And we have angles associated with them that start with the initial side and go around to that point and go around to this point. You see, and so all of these angles will give us the value that we have here. Wow, that's an awful lot of angles. How do we list the infinitude of answers for this equation? See, and actually that becomes the greater problem in some of these equations, is we can get to an answer like this. We can find the one reference angle or one or two angles that solve the equation. But then to list all of the answers that will solve the equation, that becomes the greater challenge sometimes. Now, in this one, I'm just going to show you a technique for listing them. Now, the idea is that it's a 45-degree angle, and remember that's pi over 4. So we know x is equal to pi over 4. Okay. Now, notice that this, let's see, let me erase here. If this is pi over 4 to that point, and this is, now let's see, this is pi, which means 4 pi over 4. So this is 1 pi over 4. This would be 2 pi's over 4, 3 pi over 4, 4 pi over 4. All right, so this would be 3 pi over 4. And this would be, let's see, 4 pi over 4, this would be 5 pi over 4. And this would be 6, 7 pi over 4. Now, are we going to take the time to say pi over 4 plus n times 2 pi for this one, and then 3 pi over 4 plus n times 2 pi for this one to get all of the coterminal angles associated with this one, and then 5 pi over 4 plus n times 2 pi for all the coterminal angles for this one, and then again for that one. Well, it turns out we don't need to do that because of the idea that the distance from this one to this one is exactly the same as from this one to that one, and the distance from this one to that one, and then the distance from this one to that one. You see, these are exactly 90 degrees or pi over 2 from one another. And so I can give all of the answers by just saying, all right, I'll take that first one, the pi over 4, and all I need to do is add n number of pi over 2 distances. I don't want to confuse things with this. Let me take it off. So it's n times pi over 2. Now, there are other ways of writing this. We could write n pi in the numerator over 2. We could consolidate the two fractions, and we might see it in a lot of different forms. But this is the fundamental idea, and this gives all of the possible answers for this equation. We can analyze or check our results in solving equations by looking at the graphing calculator. Let's do that now for this problem. Sometimes one of the most challenging parts of a problem is to enter the equation correctly, particularly if we're having to enter the reciprocals. Here we want to enter cosecant squared x, and we do that as 1 over sine squared x, but look at the denominator here of our fraction. This is sine x all squared, and that's how this must be entered for sine squared x. So it's in a denominator, which makes it 1 over sine squared x. Now this opening parenthesis is a default within the TI-83. This was an automatic item. I've closed that parenthesis here, and this closing is to close the opening parenthesis here. And then outside of that parenthesis, squaring to give us the sine x squared, or sine squared x notation, and then minus 2. Well, I've also created some rather interesting window settings. I have set the x minimum at 0. The x max is 6.28. This is 2 pi, roughly. And for the x scale, I have set this decimal. And the way I set this decimal was like this. I'll just go through it again here. I wanted pi over 4. I want tick marks at pi over 4 so I can see those particular distances that are important in our problem. So I can make this scale setting like this, as pi divided by 4. And then the calculator will automatically calculate the decimal equivalent. Well, let's see. The graph then has this appearance, and we know that solution points are at x-intercepts. So we're just looking for the position of x-intercepts. Now remember, we're just going through one cycle here, 0 to 2 pi. So we have an intercept here at pi over 4. Here is a distance of pi over 4 also. Here's another distance of pi over 4. Now these two together, pi over 4 and pi over 4, that's 2 pi over 4 or pi over 2. So this is the pi over 2 distance. Here's another distance of pi over 2, another distance of pi over 2, and we would see that that situation continues in either direction if we change our window settings. But here we're just verifying the infinitude of the answers that we got on the board. We've already seen from the two previous examples that in one example we had sort of a first degree trig equation. In the second one we had a second degree trig equation. And so we kind of relate those ideas back to our previous experience. And it turns out that there are a lot of different looks that trig equations can have. And it's important to get our heads into a strategy for solution by looking at the form that the equation is taking. If it takes a quadratic form, you see, then we use a certain strategy. If it has a first degree form, then we use a different strategy. And in this problem, the trick is that we have two different trig ratios involved. We have cosine and sine. And the idea is to rewrite the equation so that we have only one trig ratio involved. And there are a couple of ways of doing that. Now, whenever we have second degree trig ratios, the idea of using these Pythagorean identities should come to mind. We could rewrite sine squared x, for example, as, well, now let's see, The basic Pythagorean identity is sine squared plus cosine squared equals 1. So sine squared is 1 minus cosine squared. So we could replace sine squared with 1 minus cosine squared, and we would have this rewritten in terms of only one ratio. All right, that's one strategy. Another strategy is to realize that another identity is that tangent is sine over cosine. So we could divide on both sides here by cosine squared x and accomplish a similar kind of thing. That is, we can rewrite in terms of one ratio. All right, I've elected to do that here. I've divided on both sides by cosine squared x, and here we get 1, and here sine squared x over cosine squared x is tangent squared x. So I'll clear the coefficient here by dividing on both sides by 3, and now using the square root property, I know that tangent x is plus or minus the square root of 1/3, or plus or minus 1 over the square root of 3. All right, now, and then off we go with the evaluation process. Now, 1 over the square root of 3, and we're noticing that it's plus or minus, and that means that a reference angle in all quadrants is going to end up solving this equation. Well, let's slide over to the side and think about a basic triangle involving the square root of 3. So that was 1, 2, the square root of 3. Now let's see, we want the tangent to be 1 over the square root of 3. So that's opposite over adjacent. So we're talking about the perspective of this angle. And that's an angle of 30 degrees or pi over 6. Okay, now we jump into the idea of the circle and the angles, the various reference angles within the circle. All right, now for tangent, we know that tangent is positive in these two quadrants and negative in these two. All right, but plus or minus is involved here, so the sign pattern doesn't really make too much difference to us because we're going to be in every quadrant. So we have a reference angle of pi over 6 in every quadrant. So this is the idea. Okay, now the trick once again is to list the infinitude of answers. We know that basically x is equal to pi over 6. But a reference angle in the second quadrant is also pi over 6. And the angle associated with that reference angle is 5 pi over 6. So we know then that x is 5 pi over 6 as well. Now, how do we get to the other angles? Well, now, actually, we could go through a little discussion about the period for tangent is different than the period for sine and cosine. The period for tangent is just 0 to pi. For sine and cosine, it's 0 to 2 pi. So with the tangent, it's the idea that we have a kind of, we repeat the cycle of plus minus and then plus minus down here for the other two quadrants. So we don't have to worry as much about the whole circuit as we would with sine and cosine. But let's keep our thinking where it has been in the past. Now, I'd like to generate all of the values here for both of these reference angles. And I'm noticing here that these are sort of 180 degrees or pi distance from one another. That is, generate this one and I go a pi distance back to this one. And then I go another pi distance and I'm back to that one. And another pi distance and I'm back to this one. And another pi distance and I'm back to that one. You see, that's the idea for generating the infinitude of angles associated with that one, you see, and this one as well. And these two are 180 or a distance of pi away from one another as well. Now, we can't use the little strategy of jumping from this one to that one and then this one to this one and this one to that one. You see, we can't do that because they're not the same distance apart. This distance right here is a good deal greater than the distance right there. So we just can't jump from one to the next. So we have to use two different angles to give this infinitude of answers. Okay, so we have the pi over 6, and then plus pi, and then plus 2 pi, and then plus a 3 pi, and then plus 4 pi, and so on. Okay, so it's the idea of pi over 6 plus n pi. And in a similar way, it's 5 pi over 6 plus n pi. To take out the challenge of listing this infinitude of answers, let's limit the domain here, make things a little bit easier as we come to the answer part of our problems. The domain is limited here to 0 to 2 pi, one complete cycle of the sine and cosine curves. All right, now let's consider this problem. We have 2 sine squared x is 2 plus cosine x. Our first order of business is to try to rewrite the equation so that we have only one trig ratio involved. Well, now to do that, we have to think in terms of rewriting cosine in terms of sine, or rewriting sine squared in terms of maybe cosine squared. And when we see the squared business, that's where our attention ought to be drawn, because we can rewrite this by using the Pythagorean identity. That, remember that sine squared x plus cosine squared x is equal to 1, and so sine squared x is 1 minus cosine squared x. So I'm going to make a replacement here of 1 minus cosine squared x. And now I have rewritten the problem in terms of one ratio. And that's an important part of the strategy. All right, now it's a matter of just kind of performing operations and noticing the kind of structure that we have. And the structure is quadratic, you see. So I'm going to throw all the terms to one side and try to factor, or some kind of strategy like that. At any rate, we have, let's see, 2 minus 2 cosine squared x equals this business. And now I'd like all the terms on one side. I'll throw them to the right. I've got 2 plus cosine x over there right now, and I'll subtract 2 on both sides, and I'll add 2 cosine squared x. And now I'll clean up a bit. I see 2 minus 2, they go out. That's nice. And I'll write the second degree term first. And now my strategy would be to factor here. And if there's any confusion about how to proceed from one point to another in a problem, a lot of times what you can do is just let a foreign letter stand in for a trig ratio. Like here we could say, okay, we understand that cosine squared x means cosine x all squared. So we could let a letter stand in here like u. And so we might say 2u squared plus u. You see, and what would we do to solve for u? Well, we do the same thing to solve for cosine x. So sometimes that will help us see through situations like this. At any rate, we factor, and I'm taking a common factor of cosine x out of these two. So I have, let's see, take cosine x out of this, and I have 2 cosine x remaining. Take cosine x out of this, and I have 1. And now it's the idea that I need to find the value of x that will cause each of these factors to become 0. Remember, when we factor algebraically, we're looking for the zeros of each factor as solutions to the equation. So that's what we're going to do next. I'm going to come back here and create a little more room for myself. The factored form now, I'll just reproduce that same step over here. We have, whoops, not equals. So we have this. Now, we're thinking in terms of, okay, the value of x that will cause this factor to become 0 will be a solution to the equation. And I can make the request like this. I can say, I'd like to know the value of x that causes cosine x to be equal to 0. You see, and in a similar way, I want the value of x that will cause this factor to become 0. And we're going to end up analyzing each of these two separately. You see, that's the idea, though. All right, now, cosine x equals 0. This one is easier to evaluate thinking about the graph than thinking about a unit circle situation. We could use the unit circle situation, but it's much easier to think about the graph. Now, think about the cosine graph. Starts at the top of the amplitude, comes down and does this. And this is the position of 2 pi, and this is the position of pi. and this is, of course, 0. Now, the intercepts are the places where the cosine is 0. The cosine of that value, which is pi over 2, is 0. And at, let's see, pi over 2, 2 pi over 2, 3 pi over 2. So the x that we are after here would be pi over 2 and 3 pi over 2. Now let's solve the equation associated with the other factor. We're solving this equation. So I want to isolate cosine x on one side. I'll subtract 1 on both sides to begin with. So we have 2 cosine x equals negative 1. Dividing on both sides by 2, I find cosine x to be equal to negative 1/2. All right, now we need to analyze in some way the situation so that we identify the angles such that the cosine of those angles is negative 1/2. Well, now notice that this is not 0. In our previous factor, we had cosine x equals 0, and it's real easy to analyze the situation graphically. If we tried to analyze this graphically, look at what we would have to identify. Slide over here to the graph, and let's see, we need in the cosine curve, we would have to identify that very special point where the y value, the vertical distance, is negative 1/2. That occurs about right in here and about right in here. Now, how do we do that? We have to think about the x associated with that vertical distance of negative 1/2, and for the same way here. You see, it's real easy to identify x-intercepts, the place where the cosine of an x value is equal to 0, using the graph. But it's really difficult if we're not trying to identify intercepts. When we are dealing with a situation like this, where we have the cosine of x is some real number other than 0, the easy thing to do is to use the little reference triangle like this, and reference triangles within our unit circle diagram. All right, so this is 1, 2, the square root of 3, and from the perspective of this angle, we have a cosine of 1/2. Oh, this angle is 60 degrees, or pi over 3. Okay, now we jump into the unit circle idea. And for cosine, the sine pattern, oh, we forgot the sine pattern. Okay, if we're talking about a reference angle of 60 degrees here and a reference triangle here, then we're talking about the adjacent side over the hypotenuse for cosine. Oh, the cosine goes with the x value, because with a unit circle that's going to end up being 1. So at any rate, we have the notion of, let's see, x is positive in this quadrant and that quadrant negative in these two quadrants. So we're looking for reference angles of pi over 3 that appear in these two quadrants. Okay, a reference angle of pi over 3 in this quadrant would be this reference angle. But associated with that reference angle is this angle. All right, and a reference angle of pi over 3 in this quadrant would be about right here, because that's the reference angle, and we're looking for the angle that goes around to that point. Okay, now let's identify this angle. Okay, we have, now this is pi over 3, and this is pi, which is 3 pi over 3. 3 pi over 3 minus 1 pi over 3 is 2 pi over 3. So the angle to this point is 2 pi over 3. And like I say, this is 3 pi over 3, and another pi over 3 for this reference angle gives us 4 pi over 3. So we're talking about angles, x over here, of 2 pi over 3 and 4 pi over 3 that will solve this. Now notice that we're only identifying angles that are within the domain for our particular equation. We said that we only want x values between 0 and 2 pi, and that's why we're looking at angles in only one complete circuit of our unit circle. Okay, we have 4 answers here. This one, this one, this one, and this one. Let's see if we can identify those using the graphing calculator. Notice once again in this problem that on the graphing calculator, to enter sine squared x, 2 sine squared x, it's a 2 coefficient, and it's sine x squared. So we close the parenthesis for the x here. This is the closing of the parenthesis for sine x, and we square, and then minus cosine x minus 2. All right, the window settings are at 0 for x minimum and approximately 2 pi for x max.
And the x scale I want to set with you. Remember, we're just verifying solutions here, and our solutions have to do with fractions whose denominators are 2's and 3's. So the prudent thing to do is for us to make a common denominator of 6 and cause that x scale to be pi over 6. So I'll enter it that way, pi over 6. Now look at what happens. As soon as I cursor down to the next line, it will convert this into a decimal. Notice the y minimum is at -1 and the y max is at 0.5. All right, here's our graph. Now remember, this is an interval of 0 to 2 pi. And we're verifying our solutions. Each tick mark here is pi over 6. So this is 1 pi over 6, 2 pi over 6, 3 pi over 6. Now 3 pi over 6 would be pi over 2, and that turns out to be one of our solutions. This is 4 pi over 6, and 4/6 pi, or 4 pi over 6, reduces to 2 pi over 3, another of our solutions. And this one is, let's see, 5, 6, 7, 8 pi over 6, which is 4 pi over 3. And that's another solution. And here is, oh, I lost count. Let me go back. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pi over 6. Divide both numerator and denominator by 3. We get 3 pi over 2, another of our solutions. So we verified all of our solutions. The key here was to find that common denominator, to use pi over 6 for the x scale and not simply 1. Now incidentally, if you had neglected to change the x scale, if you had made the x scale, let's say 1, then the graph would look like this. But in order to verify solutions, we would have to use the trace option, and we would have to zoom in on the intercepts and make conversions. You see decimal conversions for our answers and so forth. So it's quite a bit more cumbersome. The easy thing to do is to make that x scale pi over 6.
This next equation involves a new twist, and the new twist is that this is sine 2x equals some value over here. Now notice 2x. If we are restricting the domain for x, that is, if we're saying that x is between 0 and 2 pi, that is, 0 is less than or equal to x and x is less than or equal to 2 pi, then what is the domain for 2x? Well, let's see. If I multiply by 2 in all three parts here, I have this. So the 2x is between 0 and 4 pi. Now, let's keep that in mind. We have to keep that in mind as we begin to identify solutions to our particular problem. Okay, so here we go. I've got the sine of some angle, and I'm not going to worry about the 2 being involved in here, but the sine of some angle is negative square root of 3 over 2. Well, let's see. I'm thinking about some kind of reference triangle here, or triangle I need to refer to in some way. This is 1, 2, the square root of 3. Let's see, the sine of what angle is the square root of 3 over 2? Oh, from the perspective of this angle, the square root of 3 over 2. Good. All right, so it would be this 60-degree angle here, and that's an angle of pi over 3 in radians. Okay, so I know I have a pi over 3. Now, I've got a negative value here, so I have to think about where I am in the coordinate plane. All right, now let's see, for the sine goes with y. All right, y is positive in these two quadrants but negative in these two. So I've got reference angles that appear in these two quadrants, and those reference angles are pi over 3. So here's a reference angle of pi over 3 in the third quadrant, and here's a reference angle of pi over 3 in the fourth quadrant. Now I'd like the complete angles associated with these reference angles for my answers. Well, let's see. If this is pi over 3, now this is pi, so I've got let's see, this is, if I'm thinking of pi over 3's, you see this is 3 pi over 3 plus another pi over 3, that's 4 pi over 3. So the angle right here is 4 pi over 3. And this one would be 5 pi over 3. All right, so those are my two angles. But wait a minute, what have I found? I have found the angles that are 2x. The sine of these two angles is negative square root of 3 over 2, but these angles are in the form 2x. So it means then that 2x is equal to 4 pi over 3. And 2x is equal to 5 pi over 3. But wait a second. 2x, you see, the 2x has a domain of, you see, 2x is going from 0 to 4 pi. Uh-oh, it's not just one complete circuit for this angle of 2x. It's two complete circuits. Oh, so I have to be careful here, and I have to go one more circuit around for the angle coterminal with this one that is in the next go-around. You see, I have to go around the circuit one more time. So I've got 4 pi over 3, and I have another answer, which is 4 pi over 3 plus 2 pi. You see, for this 2x to go from 0 to 4 pi. Okay, now, associated with this one, I have this angle, and the angle coterminal with this one more time around the circuit. So I have plus 2 pi. Well, am I finished? No, I'm not finished. I don't want to know what 2x is. I want to know what x is. So from here, I have to evaluate for x. Well, let's see. All right, x is what? Well, let's see. To find x, I'm going to take half of this and therefore half of that. You see, take half on both sides. Half of 4 pi over 3 is 2 pi over 3. And half of this business is, well, let's see, I'm taking half of both of these. It would be 2 pi over 3 plus pi. And actually, these could be consolidated before you could bring these two terms together, you see, and make one fraction out of them before going through this process. But this works out just fine as well. And for this other one, we have x is, let's see, half of this. You see, 1/2 times this side, 1/2 times this side. 1/2 over here is 5 pi over 6. And this then is 5 pi over 6 plus half of 2 pi, which is simply pi. So these then are our 4 answers to this particular problem. In this next one, very similar idea. We have cosine x over 2 equals 1 over the square root of 2. And you begin the analysis by kind of thinking like this, that this is cosine 1/2 x. Let's think about it like that. And if we're saying that x is falling between 0 and 2 pi, then what about 1/2 x? Well, taking 1/2 in all parts, then 1/2 x is falling between 0 and pi. All right, let's keep that in mind as we go through our analysis. And now we just kind of follow our nose through it as we normally would. The cosine of some angle, and we don't really care how this is expressed at the moment, but the cosine of some angle is 1 over the square root of 2. Now this was the one associated with the 45-degree angle or the angle of pi over 4. And so we're thinking about the 1/2 x then is pi over 4. Now that's in the first quadrant, but where else is cosine positive? Cosine. Let's see, cosine is associated with x, and that's the first quadrant and the fourth quadrant. Okay, first quadrant and fourth quadrant. So we have a reference angle of pi over 4 in the fourth quadrant. Now, in the past, what I have been doing is this. I've been thinking that we take our, you see, we take the unit circle, and we're thinking cosine. So cosine, the sign pattern for cosine is like this. I have a reference angle of pi over 4 in that quadrant, and also this quadrant. Actually, it's an actual angle here. It's a reference angle here. And now I'd like the angle associated with this reference angle of pi over 4. So I'm thinking about, let's see, I've got pi right here. This is 4 pi over 4. 5 pi over 4, 6 pi over 4, 7 pi over 4. Okay, this is 7 pi over 4 for that angle. Now, so those are my two angles that solve this, but remember that 1/2 x is pi over 4, and 1/2 x is 7 pi over 4. Now, I was considering one complete circuit here, but let's kind of look at our reference to our domain for the equation that we're dealing with. This says that 0 is less than 1/2 x is less than pi. Oh, the 1/2 x has to fall between 0 and pi. And this value for 1/2 x doesn't fall in there, so we need to throw that out. And this then becomes our only solution. But we're not finished, because we want the value of x, not the value of 1/2 x. So let's see, associated with this, if I multiply by 2 on both sides, I find, let's see, x to be equal to, multiply this by 2, and we have 2 pi over 4, which is simply pi over 2. This next equation is quite obviously in quadratic form. We have a second degree term involving sine x, we have a first degree term involving sine x, and we have a constant term. And we're going to use the same techniques that we would use in the past for solving quadratic equations. Our first choice would be to solve by factoring, and if we absolutely have to, if we can't factor, we have to use the quadratic formula. Now, do avoid using the quadratic formula unless you absolutely have to here, because it just creates some approximations that you don't want to deal with unless you absolutely have to deal with them. At any rate, this one turns out to be factorable. If we can't see through the factorization very easily, then we just replace sine x with a letter like n. We might think of this as 2n squared plus 3n, then plus 1 equals 0, and factor this, and then replace n with sine x, and we have the factored form in terms of what we have here. But I think we can see through this, or quite possibly we can. The factored form turns out to be, well, let's see. I'm thinking, let's see, for 2 sine squared x, it's 2 sine x times sine x, you see, like 2n times n for 2n squared. Same idea. All right, all signs are plus, and we have 1 and 1 for the factors of the last term. And we can verify the factorization by the multiplying and getting the middle term. Okay, now the idea is that we have solutions at the zeros of each factor. So we'll take each factor and set them equal to 0. And let's see, for this one, if we're solving, we'll subtract 1 on both sides, and then dividing on both sides by 2. Now let's see, let's think about sine x is negative. In what quadrants? Well, let's see where, and what kind of angle are we talking about here for this angle x? Well, let's see, for 1/2, we're thinking maybe this way. It's, remember, the 1, 2, square root of 3. And the idea that, let's see, sine is opposite over hypotenuse. So from the perspective of this angle, we have a 1/2. 30 degrees, or pi over 6. Okay, so we have an angle of pi over 6. But the sign of the angle is negative. Now, in what quadrants does that take place? Well, let's see. We've got, let's see, sine corresponds with the notion of y, and so we have the plus, plus, minus, minus. So sine is negative in these two quadrants. So we have a reference angle of pi over 6 in this quadrant and in that quadrant. Now, what are the angles associated with these two reference angles? All right, well, we think about pi here. Now, pi in terms of sixths is 6 pi over 6. And 6 pi over 6 plus 1 more pi over 6 is 7 pi over 6. So one solution is 7 pi over 6. So x then is, I need a place for it here. Let's see, x is 7 pi over 6. And then for this other one, well, let's see, all the way around would be 2 pi, and then we want to subtract pi over 6. Well, let's see, 2 pi in terms of sixths would be, I'll take 2 pi and multiply by 6 over 6. That's 12 pi over 6 all the way around. Subtract 1 pi over 6, that's 11 pi over 6. So the other one is 11 pi over 6. All right, so that's 2 of our answers. Now, let's find our other answers. We march over here. Sine x is plus 1 is 0. So sine x then equals -1. Aha. Now, I mentioned before on a previous problem, we said that if the cosine of an angle or the sine of an angle were 0, then it's a little easier to look at the graph. And it turns out that looking at the graph is easier as well when we are either at the top or the bottom of the amplitude. We can just see it more clearly. We can see it using the circle, but it's real easy to see if we are looking at the graph. Oops. I'm going to do the graph differently if we're looking at the graph. Now, for the sine curve, let's see, we start at an intercept and we end up at 2 pi, and the critical values are here and here, and we start here, we go to the top of the amplitude, bottom of the amplitude, back to, there we go. All right, so now, sine of what angle is -1? Well, -1 occurs right here. Oh, that's at this point. That's between pi and 2 pi. That's 3 pi over 2. You see, so that's kind of the way that you think your way through that situation. So our third solution is x equals 3 pi over 2. Our 3 solutions then to that original equation. Consider this problem. The technique I want to illustrate here is that we kind of bump into a brick wall when we try to take an equation like this involving 2 different ratios, and we want to rewrite it in terms of one ratio, and yet both of them are first degree. It turns out that it's easy to rewrite them if they were second degree. So the technique that we use here is to square on both sides. Now, and we'll show all of that business right here, but remember before when we squared on both sides to solve equations, we had to do that when radicals were involved. And when we square on both sides, sometimes we create extraneous solutions. So it's really important to take those values that we find and put them back into the original problem to verify that they are indeed solutions. All right, so we're going to do that at the end of this problem. But the first order of business is to square on both sides. And squaring here, you see, we get cosine squared x plus 2 cosine x plus 1. Squaring over here, we get sine squared x. All right, now we can rewrite fairly easily in terms of one of the trig functions. Now, I am choosing to rewrite sine squared x in terms of cosine squared x and not the other way around. If I take this term and write it as 1 minus sine squared x, I'll still have a cosine situation in the equation, you see. But if I take sine squared and write as 1 minus cosine squared, you see, and now all of the ratios are in terms of cosine. All right, and now I recognize this as a quadratic situation, so I'm going to throw all the terms on one side and attempt to factor. Now, I've skipped a step here. I want to show it to you. I added cosine squared on both sides to eliminate this, and when I add cosine squared over here, I get 2 cosine squared. Also, I subtracted 1 on both sides, and when I subtract 1 over here, the constant goes out, so I just bring down this term. All right, now, a common factor in these 2 terms is 2 cosine x. I snag 2 cosine x out of this term, and I'm left with cosine x. I snag 2 cosine x out of this term, and I'm left with 1. And now I set each of the factors equal to 0 and evaluate. If I set 2 cosine x equal to 0, then cosine x is equal to 0, dividing on both sides by 2, you see. And so I want the angle whose cosine is 0, and we're going to identify that using the graph. And over here I have, let's see, cosine x plus 1 is equal to 0. Subtract 1 on both sides. I find cosine x to be -1. Aha, the bottom of the amplitude. So again, I want to evaluate this using our graph. So I need a cosine graph, and I need the place or places on the cosine graph where the graph is at 0 and at -1. And I need to identify the x values associated with those points on the graph. So over here, I need the, let's see, we have a 0 at pi over 2 and another one at 3 pi over 2. So we're saying then that the x that solves cosine x equals 0 is pi over 2 and also 3 pi over 2. Now let's see, the other equation said cosine x is -1, and that occurs right here, and the x associated with that is at pi. So pi is another solution, or perhaps I should say possibly another solution. Now we need to check these. That means we need to put them into the original equation. I'll rewrite the original equation right here just for handy reference. It is cosine x plus 1 equals sine x. Now, it turns out that to evaluate this, we can also use a graphical approach. Now, to evaluate the sine of x's taken on by these three values, it's easy for us to create the sine curve. Now, we either can do it down here or we can just overlay it up here. I think I'll just overlay it up here. You know, the sine curve starts at the bottom, starts at an intercept, goes to the top of the amplitude, back to the intercept, bottom of the amplitude, and back to the intercept. So the graph then looks like this. All right, so there's the sine curve. Now, let's evaluate for pi over 2. Cosine of pi over 2, let's see, here's pi over 2, here's the cosine curve, oh, that's 0. So on the left side we have 0 plus 1. The sine of pi over 2 is at the top of the amplitude, that's at 1. So 1 equals 1, yes, so this is a valid solution. All right, what about 3 pi over 2? Take a look at it. Now here's 3 pi over 2. Now look at sine and cosine. Well, let's see, we've got cosine of 3 pi over 2 is here at the intercept, that's 0. And then I'll bring down this plus 1. The sine of 3 pi over 2 is down here at -1. Is 1 equal to -1? No! So we don't have a solution here at 3 pi over 2. We have to throw that out. Now what about pi? Well, let's look at it. Let's see it. Pi, cosine of pi is pi, it's 0. Oh, excuse me, it is not 0 for cosine. I'm reading the wrong graph. So the idea is to be very careful in the evaluation process here. It's easy to make a mistake. Cosine of pi over 2, cosine of pi is at, here's the cosine curve, is at -1. So -1 plus 1, that's going to be 0 on this side. What about the sine of pi? The sine of pi, here's the sine curve, oh, it's at 0. 0 equals 0. This is indeed a solution. So these then are our two solutions to the equation.
Here's a problem involving a trigonometric equation. A batted baseball leaves the bat with a velocity v equals 100 feet per second and is caught by an outfielder 300 feet from home plate. Now that distance from the batter to the outfielder is called the range here in this problem. Let's continue. Find theta if the range of the projectile is given by this equation. R, the range, is equal to 1 over 32 times v squared times sine 2 theta. Well, here's what's happening in the problem. Now notice the position of theta, the amount we're looking for here, and at 300 feet, the distance from the batter to the outfielder. All right, here's what we know for our equation. We know that the velocity is 100 feet per second and the range is 300 feet. We simply replace these amounts into our equation. Replace v with 100 and replace r with 300. Now we need to clean up a bit. What we'll do is clear the coefficient of sine 2 theta on the right side of the equation. To do that, we'll first clear the fraction on the right by multiplying on both sides by 32. Then, of course, we'll square the 100. That'll give us this. Now we'll divide on both sides by 10,000, and we've isolated sine 2 theta on the right. Now we take the inverse sine on both sides. On the left, you see, with the calculator, we would enter 0.96 on the calculator and hit inverse sine. And what we would get, of course, is 73.74, rounded to 2 decimal places. On the right, when we take inverse sine, we're left with simply 2 theta. Well, now dividing on both sides by 2, we find theta to be approximately 37.